What is the nature of light? Is it wave or particle? Don't answer just yet, unless you are sure what's the difference between the two. Look, anything that occupies a well-defined position in space can be called with complete confidence a particle. The device on which you're watching this video right now is a particle, or consists of a very huge number of particles to be more precise, and that's why you are able to hold it in your hands. A wave is quite the opposite. It does not occupy a well-defined position in space. You cannot hold it in your hands, and of course it can cease to exist. It's only a disturbance that travels through a medium from one location to another. Remember, the key word here is medium, such as water, which without it you wouldn't be able to have this, or air, which what's allowing my voice to reach your ears. That's why watching this video in space is not a good idea, because my voice wouldn't be able to find the medium through which it can travel to your ears. And in case this video finds you in space and you couldn't wait till you come back to Earth, turn on the subtitles and you're good to go. As you can see, in the vacuum of space you are not able to hear my voice because it's a wave, but at the same time you are still able to watch the visuals, and that should make it easy for you to decide that light is particle.
Light is both a wave and a particle, and neither. Until we make an observation, the photon exists in a state of uncertainty, governed by laws of probability. And when we do observe it, it becomes something completely different.
So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Does that sound logical to you?
No, sir.
Of course not. And according to my esteemed colleague, the particle does not exist at all until we observe it.
Wait a second. Where are the waves?
You have two ways, and two ways only if you want to carry energy from one place to another. First, you can do it by transferring energy from particle to particle, or by making the particle carry the energy within itself. For example, when you throw a basketball. Now, the basketball has what is known as kinetic energy, and since light is a form of energy, we had to pick which way this energy is reaching us. Is it through waving or as a form of kinetic energy? For more than 100 years, people believed in the particle proposition simply because it was proposed by Isaac Newton. And since his laws of motion and theory of gravity were right, people assumed that he was also right about light, using light's ability to travel in space and based on his laws of motion. He deduced that only particles he called corpuscles can describe why light travels in straight lines. He also noted that light didn't seem to exhibit diffraction characteristics. If light was a wave, we would be able to see it even if there is a physical barrier blocking the source, just like how sound travels around physical objects to reach our ears. But as it turned out, light does actually refract, and Newton's theory had no explanation for that. It also doesn't have an answer for why the source that emits particles doesn't shrink in size, or why we don't see any interaction when the particles of two different sources of light meet. And most importantly, why can't we store light in cans? There was this widespread belief that the universe is filled with a massless transparent substance called ether, and the Dutch physicist Christian Huygens, who's considered a major figure in scientific revolution, believed that light is made up of waves that are using ether as a mean of propagation. His wave theory succeeded in explaining most of the phenomena the particle theory struggled with, but it failed to penetrate Newton's prestige, and the corpuscle theory of light remained mainstream for more than 100 years, until Thomas Young was able to finally have it discarded thanks to his infamous double-slit experiment. He cut two slits in a sheet of metal and shined light through them into a screen. Now we have two possible scenarios. If light is a particle, the result is very simple. You will find two lines on the screen in front of the two slits, as though he is firing marbles through a wall with two slits in it. But if light is a wave, what will happen is completely different. The screen will show an interference pattern, because once a wave of light passes the two slits, it will split into two new separate waves, and then you would expect these two new waves to interfere with each other. If the peak of one wave meets the trough of the other one, they will cancel each other out, leaving a dark spot on the screen. This type of interference is known as destructive interference, the opposite of which is constructive interference, which takes place when the waves meet trough to trough or crest to crest, resulting in the bright lines that appear on the screen. And guess what? Thomas Young's screen depicted an interference pattern, which means light traveled as waves. Then in 1818, a strong believer in Newton's theory named Simeon Poisson showed if light was a wave and you place a spherical object in front of it, you have to see a bright spot at the center of its circular shadow, which he considered to be absurd, and you cannot blame him for that, because no one has ever encountered a circular shadow with a bright spot at its center, caused by the diffraction of the beams of light that hit the curvature of the spherical object. Eventually an experiment had been performed, but with a single wavelength of light, and the bright spot Poisson considered absurd manifested itself at the center of the circular shadow, symbolizing the final nail in the particle theory of light scattering. Or at least that's what we thought for a little short amount of time. Once the wave theory of light was able to finally prevail, new pieces of evidence pops up in favor of the particle theory. It started with this man right here who was studying black body radiation, and to be able to make sense of his observations, he deduced that light can only travel in discrete pockets of energy he called quanta. Max Planck didn't realize the significance of his finding. He thought the concept of quanta was just a mathematical trick to make his theory match the experiment. And how can you blame him for that? Because believing energy is not a continuous flow of particles is analogous to believing that you can only be 10 years old, or 20 years old, or 30 years old. You got the point, but not any age in between.
1 minute. Yes. Good. Well, everyone believes that light is a wave, yes? Well, I can prove that when a light ray is propagated from any point, it consists of a finite number of energy quanta which can be produced and absorbed only as complete units. That only took 10 seconds.
25 years after Max Planck rose the particle theory from its ashes, Albert Einstein won his first and only Nobel Prize. It was neither for the special nor for the general theory of relativity. It was for settling this debate once and for all. Planck was right. Light comes in discrete pockets of energy called photons. It's a particle. But at the same time, each of these photons consists of an electromagnetic wave oscillating back and forth, which will take us back to Young's double slit experiment. But this time, instead of shining light into the two slits, we will fire one photon at a time and see how it will behave. At first, the photons that made it through the slit started showing up at random places on the screen. But as we kept firing more and more photons, the unimaginable happened. The photons didn't show at random places as it appeared at first. Instead, they were well organized to show the interference pattern. But it's impossible. How can we get an interference pattern when we are shooting one photon at a time? It's one photon. It doesn't have anything to interfere with. Remember, to be able to get an interference pattern, you need a wave that would split into two new separate waves when it passes the two slits. One photon will go from either the left or the right slit. It can't go from both unless it managed to somehow split itself between the two slits and interfere with itself. To see if this is the case, we will keep an eye on the photons before they go through the slits. But unfortunately, nothing unexpected happened. 50% of the photons went through either slit. So everything went exactly how we pictured the experiment in our heads. Except this time when we looked at the screen, we didn't find the interference pattern. Instead, we found two lines on the screen, the ones you would get from firing particles. We tried to outsmart light by firing two entangled photons, one directly to the screen and one to our detector. The photon knew that his twin brother was being watched and refused to show the interference pattern. And you know what's even crazier? We waited for the photon to hit the screen and only then we picked at the one it's entangled with. But as you can see, the photons don't acknowledge the existence of time. This experiment has been repeated over and over again, and the outcome is always dependent on whether we are looking or not. If you don't look, an interference pattern appears indicating that the photon is actually a wave, but once you decide to observe its path, it changes its mind and tells you I am actually a particle. And just like that, Young's experiment left us with two daunting results that seem to defy common sense. Fire. For thousands of years, nobody knew what it actually was, but that didn't stop humanity from benefiting from it in every way, shape or form possible. Quantum mechanics is taking us through a similar path. We currently don't have a smart or satisfying answer for those daunting results we got, but we do have a collection of views about the meaning of quantum mechanics, known as the Copenhagen interpretation of quantum mechanics. In this new world, a photon doesn't occupy a definite place in space. Instead, it exists as a wave, but not a mechanical wave, nor an electromagnetic wave. It's a probability wave, meaning that the photon occupies all the places it has the possibility to occupy, all at the same time. Whereas in the case of the double slit experiment, the photon went from just the right slit and from just the left slit, and from both of them, and from neither. All of these possibilities are in superposition together, as long as we're not looking. But if we try to look for it, the wave function collapses and the photon occupies a definite place in space. Which place exactly, and where is the photon right now? These types of questions are forbidden in quantum mechanics. You are not allowed to ask where is the photon right Wait now, you are only allowed to ask if I look for the photon in this little particle part of space, what's the possibility of finding it there? If the photon has 10% chance to be at a certain place, it will show up in 10 occasions if you repeat the experiment 100 times. If you are getting baffled by that, don't worry, you are not the only person.
And it allows us to make use of the quantum world.
The goal of scientific pursuit should not be merely to make use of the world around us. It should be to understand it, fundamentally.
I wonder what would his reaction be if he heard about the many-world interpretation of quantum mechanics, which proposes that there is no such thing as wave function collapse. Instead, with every measurement, the world splits into multiple realities, where every possible scenario is realized. I know what you're thinking. Maybe light is this weird phenomenon that no one seems to understand yet. I hope you're ready for this, because we have performed this experiment using electrons, neutrons, protons, and even atoms, which you and I in this whole universe are made of, and the results were no different. If you are not looking, your screen depicts an interference pattern that disappears the moment you decide to peek, which begs the question, what is the nature of matter? Is it particle or wave? A wave of what?
Just watch where you're going, please.
Why should I? Why should either of us? According to you, if that automobile was a particle, but we didn't see it, it wouldn't have been there at all. We would be perfectly safe.